Hi, and welcome to Always Eclectic Stacy. This is Always Eclectic Chemistry, and we're in our ionic bonding series. And in this video, you're going to learn how to balance ionic compounds. Come on, let's go. Hi, and welcome back to Always Eclectic Stacy. We're still working on ionic bonding, and the next big question is, how do you predict the number of atoms in an ionic bond? Which leads to the question, or the big concept of, how do you balance an ionic compound? There are several ways of doing this, and we'll talk about the basics, and then I will model for you both the Criss-Cross method and the lowest common factor method, and you can choose which one works best for you. Okay, the first thing to remember when we're talking about how to balance ionic bonds is the octet rule. Atoms will tend to gain, share, or lose electrons in order to acquire a full set of valence electrons. So for this, we're primarily looking at the valence shells of electrons. And please remember, metals are positive because they're cations, and cat has paws, meow, meow, meow. And anions are going to be your negative ones, and they will be gaining the electrons. So positive lose the electrons, they give their electrons to the anions. And you can determine it a number of ways. So you can determine it mathematically or through the Criss-Cross method, which I will be modeling for you now. Okay, let's start with sodium chloride. So the first thing I always do is I underline or highlight my different parts. So sodium is my cation, so I'm going to underline it in red. And chloride is my anion, so I'm going to underline it in orange. Then the next thing I do is I go ahead and I write down the ion of each of these elements. So sodium is in column 1, which means it has a 1 plus charge, so it's Na 1 plus. Chloride is in column 17, and you look at that because you look for an element that starts with chlor. If you're unsure, you can go ahead and remember our non-common or very common non-metallic roots. It's a video that I have, and so that is Cl1 minus. And this is where we talk about the first trick. So you can either do the Criss-Cross or the LCM model for this, but a big rule is when they each have the same charge, so when they each have the same charge, 1, 1, so I'm going to write charge number to be very specific because they are opposite, they cancel each other out. So this can be 1 and 1, 2 and 2, 3 and 3, 4 and 4. So what you do is when they cancel each other out, you just take the charges away and you make the compound. So that becomes NaCl, because you only need 1, 1, and 1 of each to balance out the charges. So I started with a pretty easy one. I'm going to write a very quick some other examples that you may see out there that go along right with this. So you have magnesium oxide, and so magnesium is our cation, and it's Mg2 plus. Oxide is our anion, and it's O2 minus. So you got the 2 and the 2. They cancel each other out. You don't have to balance them, so it just becomes MgO. And one more very quick example on this could be aluminum phosphate. And if you're unsure about the polyatomics, go ahead and reference my video on the common polyatomic ions. That'll help you. And I'm just showing that this works for both monatomic anions and polyatomic ions. So aluminum is Al3+. Phosphate is PO4, 3-. You got the 3 and the 3. They cancel each other out. So it goes Al, PO4. Okay, let's jump into some more of the more difficult or where you have to do some work examples. Be right back. Okay, now let's balance lithium oxide. So remember, the first step is to always identify your cation and then your anion. Lithium is my cation, so I'm going to underline it in red. And oxide is my anion, so I'm going to go ahead and underline that in orange. The lithium ion is Li1+. This is in the first column. Li1+. I can write today, I promise. And oxide is O2-. Now we're looking at that, and we know that 1 and 2 are not the same. So now you can go ahead and see, do you want to do your LCM or your Criss-Cross? And I modeled both for you to show you that they both work. So for LCM, which is one that most of my students really appreciate because it visualizes and then automatically reduces it for you, which sometimes is that extra step on the Criss-Cross that they struggle with. You're going to go ahead and take just the charge numbers and write them out here. So I have 1 and I have 2. So I have 1 and 2. And then you know what they're for, or you can go ahead and if you want, you can write Li and O out here sometimes this way. So Li is 1. So you're going to make a math equation. You're going to go 1 times my subscript equals. I'm going to do the same math equation for O. 2 times my subscript equals. Now, if you're wondering what they're going to equal, it's going to be the smallest whole number that they can both go into. So for 1 and 2, that whole number is 2 because you don't want fractions. So this number becomes 2. So then you solve the math equation. 1 times what equals 2? Oh, that's 2. 2 times what equals 2? Oop, that's 1. Okay. Now you can go ahead and write your equation, and these become your subscripts. So it becomes Li2, and then you write O, and you do not have to write 1 as a subscript because you've already written the element 1 time. Now, for Criss-Cross, you can actually look at this and see the Criss-Cross happening, which is pretty cool. You're going to go ahead and you're going to write them both down. Li1+, O2-, and you're going to cross the charges. So this superscript on Li becomes the subscript for oxygen. And this superscript of oxygen becomes the subscript for lithium. So it becomes Li2O. But with this one, you have to ask yourself, do I need to reduce? Can I make this any smaller? If the answer is yes, you need to reduce more to get the lowest whole ratio of subscripts possible. Otherwise, you don't have to. And if you actually look over here, you can see the Criss-Cross happening. The 1 from lithium became this number here for oxygen. The 2 from oxygen actually became this number here for lithium, and you could see the Criss-Cross happening. It was pretty cool. Okay, let's try another one where you might be able to see where the reduction can take place. So let's do copper 2. Now, remember, with the transition metals, you write the charge in Roman numerals. So 2 capital I's means a 2 charge. And I put that with silicate, just so you can see some of the more tricky ones while we're working through these. So copper 2 silicate. So remember, the first thing we do is we underline and determine which one is our cation. Copper 2 is our cation, so it's Cu, and this copper has a charge of 2+. If you're struggling with knowing that, you can go ahead and review our common metal ions, and they have a lot of the transition metals in them, like copper 1 or copper 2, nickel 1 or nickel 2. So you can go ahead and see how they work. And then you have silicate, which is our polyatomic, and it's SiO4, 4 minus, and we're going to do this in two different ways. Again, we're going to do both the LCM and the Criss-Cross. I'm going to show you how you can get the same answer using either of these methods, and you're just going to have to choose which one feels most comfortable for you. They're both completely acceptable to use either one. So for LCM, I'm going to put the copper over here. I'm going to put the silicate under it. And I'm going to go ahead and set up my equation. Copper has a charge of 2. So 2 times something is going to equal my lowest common multiple. And for silicate, it's going to be 4. And it's going to be 4 times something is going to equal my lowest common multiple. Between 2 and 4, my lowest common multiple is actually 4. So then you just fill this in so it's true. 2 times 2 equals 4. 4 times 1 equals 4. So I end up with Cu2 SiO4. Okay. Now, if we had needed more than one of silicate, SiO4, you would have had to put it into brackets and put the subscript outside of it. But luckily for this next crisscross, you'll be able to see that because we actually have to do that in one of the steps. So for this crisscross, you're going to do Cu2+, and we're crisscrossing it, or making a compound with SiO4, 4 minus, and that's silicate. So the first thing is this 2 superscript of copper becomes the subscript of SiO4, and this 4 on silicate becomes the subscript of copper. So we start with Cu4, and then we need more than one right now of silicate, SiO4, so you're going to put that in brackets or parentheses, SiO4, and right now we need 2 of them. And then we ask ourselves, can we reduce? Because for crisscross, it is not balanced until you ask yourself, can I reduce? And this answer is yes. 2 and 4 can be reduced into 1 and 2 because you can divide each by 2, and we're going to do that. So Cu, 4 divided by 2 is 2, and then 2 divided by 2 is 1. So we could take the parentheses away because we only need 1 of silicate. So it becomes Cu2 SiO4 for the balanced compound. Okay, thank you so much for watching Always Eclectic Stacy. If you like this content, please do not forget to like and subscribe, and check out some of our other videos. Thank you so much. Have a great day.